In this next segment, we want to consider an example where we have the equations x equals sine t, y equals sine squared t, and we want to think about what curve this set of equations will traverse. And one way to think about it here is if we were to eliminate the parameter, we could easily, for instance, replace the sine t in this equation, right? Y equals sine squared t. We can replace the sine there with x, because we know that x is equal to sine t. So what I can do is I can replace this sine t with x. So our parametric equation is really the Cartesian equation of y equals x squared. Now the next question is, how is the path of y equals x squared being traversed? Well, one thing to keep in mind is that for both sine and cosine, they will only take values that are between -1 and +1. And in particular, sine squared t is of course only going to be between between 0 and +1. With that in mind, let's think about what happens now for this curve. Let's say we start with t equals 0. Well, that would start at the origin at 0, 0, because both the x and the y would give me sine of 0, which is 0. And let's go to pi over 2 from there. So we know at t equals 0, we get the point 0, 0. What would be the point at t equals pi over 2? Well, it looks like here sine of pi over 2 is 1, so we would be at the point 1, 1. Okay, so from t equals 0 to t equals pi over 2, it's gone up the curve y equals x squared from 0, 0 to the point 1, 1. And then what happens at t equals pi? Well, that's going to, again, bring me back to the point 0, 0. So in fact, it traveled from t equals 0 to t equals pi over 2 to bring me to the point 1, 1. And then at t equals pi, it's going to return back to, so we can imagine it's going to just switch directions, and it's going to return back to the origin at 0, 0. So it's going to change directions and traverse the same path again, but in reverse direction there. So at t equals pi, it's going to return back to the origin. And then let's try one more point. Let's try t equals 3 pi over 2. Well, now that's going to give me the point -1, 0. I'm sorry, -1, 1. And so we see there for that part of the curve, it's going to go from 0, 0 up to -1, 1. And it's going to traverse it in that direction. And then finally, if we were to go all the way out to 2 pi, well, that'll bring it back to the point 0, 0. So in the final portion of it there, you can imagine it returns back down that same path to where it began at 0, 0. So the curve that's formed here is just this portion of the parabola y equals x squared. But in this case, because it's sine t and sine squared t for the x and the y coordinate, it's going to oscillate between those 2 points there at 1, 1 and -1, 1, back and forth. And we can see that as t increases, it's just going to essentially bounce back and forth between that point there on the right and that point there on the left. It'll never go outside that range because, of course, we know that sine t will never grow bigger than 1. And it'll never grow smaller than -1. So it'll always be trapped in that region between -1 and +1 on the x-axis, and then 0 to 1 on the y-axis. One important example that we will come back to several times while we're studying parametric curves is the example of the cycloid. The cycloid is a curve that's traced out by following a point on the rim of a wheel. Okay, so we can picture it here. You imagine this wheel is revolving, and we're following some point that's on the edge of the wheel. So as the wheel rolls, it's going to trace out this path. And this is the path that is called the cycloid, or this curve is called the cycloid. Okay, so how do we find the parametric equations of the cycloid? Well, let's think about the picture that we have here. The way we want to parameterize our cycloid is we use the angle theta as the parameter, where theta represents the angle through which this circle of radius r has rotated. So imagine we're going to follow this point P on the circle, on the wheel. So starting with the circle in the position where that point P is at the origin, and supposing now that wheel has rotated through the angle theta. Now that point P is up here, what would be the coordinates of this point? So we can look at it now where the distance that the wheel has moved along the x-axis can be thought of as the same distance that is along the arc of the circle. Okay, and we know the arc of the circle there can be just given by the radius times the angle theta, r theta. And that would essentially now give us the length of this line segment here from the point O to the point T would be r theta. And now we can think of the triangle that's formed here with the angle theta, where the radius r is there from the point P to the point C. And if we're taking the sine of theta would be the side that's opposite of the angle theta. So we would have the length of this segment PQ would be r sine theta. So with that, now we can see that the x-coordinate of our point P is going to be the difference between OT minus PQ, right? Because those two lengths, when we subtract, would give us the distance there for x. So we can see x is just OT minus PQ, which is going to be r theta minus r sine theta, which gives us r times theta minus sine theta. So that's how we get the x-coordinate of our parametric equations. For the y-coordinate, well, let's consider now we've got this distance from the point C to the point T is the radius of our circle. So you can see CT is really just r, would be the whole length of that. And then let's consider the side of this triangle here, which is just r times cosine of theta. And so the y-coordinate there would be the difference between r and r cosine theta. So we can see y would be CT minus CQ. Where CT is just the radius r, minus CQ is r cosine theta. So that gives us r times 1 minus cosine theta for the y equation of our cycloid curve. Okay, so with these equations here, we get the cycloid curve that as the parameter theta, here theta is our parameter. It's like the t parameter, but here we're using theta because it's representing the angle through which our wheel has rotated. So in this next example, we're looking at investigating the family of parametric curves with parametric equations x equals a cosine t, y equals a tan t plus sine t. So you can imagine here what this family of parametric curves gives us is a variety of different parametric curves depending on what constant a we choose. You can imagine, for instance, if a equals 0, we would just have the parametric equations x equals cosine t, y equals sine t, and we actually know that's the equation of the unit circle. If a equals 1, for instance, we would have a different set of parametric equations. X equals 1 plus cosine t, and y equals tan t plus sine t. And because maybe we want to look at how these curves change as the parameter a changes, or as the constant a changes, we can use some software to help us out. So what I'll do is I'll put these equations into a program called GeoGebra, and then we can sweep through a variety of different values of a to visualize how these curves change. So you see here in GeoGebra, I've plotted the x equals cosine t, y equals 0 tan t plus sine t. And I've put the value that we called a into a slider. So now if I move this slider around, it'll give me the same parametric equations, but assigning a different value to a. So for instance, if I move it a little bit to the right here, we can see that now with a equal to 0.6, right? So we have 0.6 plus cosine t for the x, y equals 0.6 tan t plus sine t. We get a slightly different curve here. Notice it's got a loop, and it's got this almost vertical type of curve there for the right-hand side. And as the parameter t increases, notice we get slightly smoother, more vertical looking curves. Let's sweep it now to the left. So coming back to a equals 0, we see that it kind of forms back into a circle here when a equals 0. And then now going to negative values of a, it looks like it's going to symmetrically transform the graph in a similar way that it did as we moved it to the right. So it gets more and more vertical as it moves to the left, forming almost vertical curves there. Oops. So sweeping between these different values of a, we can see a variety of different members of the family, and we can also kind of see how the parameter a affects the curve. So in fact here we can watch sort of like a movie as these as the parameter a sweeps through some different values. One more time. Okay, and you can see what's actually happening here is that when, for instance, we have 1 plus cosine t and 1 tan t plus sine t, it's going to form this little point here at the point 0, 0. And then it will form a little inner loop when a is less than 1. When a is bigger than 1, it's going to start to smooth out that little point. And as a gets bigger, it gets more and more smooth on either side. And then the same sort of pattern happens when we move it to the left. It has that inner loop. When a is less than 1, when a is equal to 1, then it's got, or a is equal to negative 1, it's got that little point there at 0, 0. And then when it's less than negative 1, it gets smoother and smoother and more vertical as it goes to the left.